So good afternoon, dear students. Today we will study about the design aspects of induction motor. So sorry. So so basically, the main purpose of designing an induction motor is to obtain the complete physical dimensions of all the parts of machine as mentioned below to satisfy the customer satisfactions. Okay, so that means uh, see, the design of any rotating machine or any electrical machine is under uh, the electrical standards basically, right? So no design is beyond electrical standards. That means one has to follow the electrical standards while designing, manufacturing, fabricating the electrical machines, right? So now that means the prime purpose, prime objectives of, or you can say the major considerations in designing electrical machines are the economy, means the money aspect, economical aspects, and standards, and one very important aspect is the customer satisfaction, customer specifications, customer satisfaction both. So basically, like if I am a machine designer and you are the customer, so you will tell me that you need a machine, an AC motor for this particular purpose, wherein your machine, wherein your current requirement are like this much ampere, the voltage where machine will operate is this much volt, torque you need is this much. Okay, so everything you will tell. So based on this, the designer, means me, let us say, will think of a design. And here one thing which is also very important is the cost. So because the vendor can say, or the customer can say that I can pay you only this much for this machine, and the designer can say, no sir, for this particular specifications the cost will be, let us say, 2 lakh, but the customer will say like, I'll pay this one. So there has to be negotiation, that is a different thing. Okay, so the designer will think from every angle how to get an optimal design. Now, when I say optimal design, I mean to say that there has to be a trade-off maintained between various factors. For example, if you will design a machine with quality material, now of course the cost of such machine will go high. Okay, so that may be possible, it may be possible that the cost, the customer may not be able to afford the cost. Okay, so there has to be a trade-off between the quality of the material used and the cost, and also the performance of the machine should not be sacrificed for this. Okay, so that means there has to be a trade-off between cost, the material, the performance of the machine. Okay, so for a good performance machine, obviously the cost will be high, the material will be high. So you cannot have a very good performance machine with poor material. Okay, and you cannot have a cheap or a low cost machine for with a very good quality material, right? So when I say optimal design, means it has to be optimal in every aspect: optimized cost, optimized design, optimized performance, right? So the following design details are required for designing the machines. The first is main dimensions of the stator, then details of the stator windings, design details of rotor and its windings, and performance characteristics. So for AC motor, basically these 4 design details are required while designing an AC motor. You need to know what should be the dimensions of stator. You need to know what should be the dimensions or details of the winding on the stator. Okay, and about rotor as well as the performance characteristics. So in order to get the above design details, the designer needs the customer specifications such as, so as a designer, you need to know the rated output power. This is what I was saying, that the customer will tell that I would use this machine in this particular application, which will operate under this much voltage, this much what should be the torque. Okay, so everything customer will tell. On the basis of that information, designer will think of a design and come out with an optimized design of machine, right? So in addition to these details, as mentioned here, the designer must have the details regarding design equations based on which the design procedure is initiated. Now, design equations, customer cannot give you design equations. It is from the designer only. So customer can give you the minimum information wherein the customer would use that machine. So rest of the thing the designer has to think of. Designer has to take care of the design equations. Designer has to take care of the information regarding various choice of various parameters. What parameters should be selected? For example, if you want high electrical loading, so in that case the size will get affected. The losses may increase because high electric loading means high current. So that may increase the losses also. Increased losses will degrade the efficiency and performance of the machines. So which parameter has to be selected? What should be the range of that parameter? What should be the value of that parameter, which is important in designing a machine, that a designer will take care of. And while designing the machine, designer will or must keep the standards in mind, right? Design standards. Information regarding the availability of different materials. So what all materials are available to the designer? Okay, so the fan which you see basically nowadays, the ceiling fan, it has copper winding as well as it has uh, aluminum winding also. Though, so the fans which have copper winding on rotor, they are costly, and fans which have aluminum winding are cost effective, low cost, cheap, right? So the limited values of various parameters such as iron copper losses, no load current, power factor, temperature rise, and efficiency, right? So because all these things are correlated, so that is what I said, that optimal design means you have to take care of all these things to get an optimal design, right? So now the output equation of an induction motor. So similar to DC machine, in DC machine also we have studied the output equation. So here also we have the output equation, and the output equation is basically a mathematical expression which gives the relationship between a mathematical relationship between various parameters, including physical and electrical parameters of the electrical machine. So it is basically the output kVA of the machine, or not kVA here because it is a motor, so it is a load basically, it will dissipate the power, so it is output kilowatt, right? kVA is for the transformers generally, right? So consider an M phase machine with usual notations. Usual notations means whichever standard notation is used for a multiple phase induction motor, so those notations to be used. So the output kilowatt, output Q, here Q is basically used for the output power, right? So output kilowatt, because the power here will be dissipated, the electrical power basically, the electrical power is dissipated by the motor, so it is in kilowatt. So output kilowatt is the input supply, input basically volt amperes, and the efficiency of the machine, right? So this will give you, for a single phase machine it is VI cos phi. For multiple phase machine it is into M. So if it is a three phase machine, you will multiply it with 3. If it is a single phase machine, you will multiply it with 1, right? Into 10 raised to the power minus 3, because you are measuring it in kilowatt. So that is why it is used. Generally the rating is in kilowatt only, right? So input to the motor. So what input we give to the motor? We give electrical input to the motor. So for example, it is a three phase machine. So this will be the input. This is the input to the motor, right? Okay. So for a three phase machine, instead of M, we have used 3 here. So now the standard assumptions have been taken here. You can see the assumptions are like VPH. What is pH here? It is for phase. Okay, VPH is the phase voltage, IPH is the phase current, right? So here VPH is equal to EPH and VPH is equal to, so here this equation, you know this, because your three phase induction motor, yesterday also we were discussing, its equivalent circuit is similar to that of a transformer, right? So that is why the induced EMF on the conductors basically is given by 4.44 F phi TTH. So number of turns of the winding into kilo into kW. So here kW is the factor basically, right? So this is from the, it is similar to that of transformers equation, right? So from here you have this value. So and the frequency is basically P ns by 120, where ns is the RPM, synchronous speed in RPM, rotation per minute, and small ns is basically in RPS, rotations per second, right? So the output kilowatt will be equal to, by substituting the values here, sorry, here in this equation. So input to the motor into efficiency. So by multiplying and putting all the relevant value here, you'll get this equation. You can see here the input to the motor is this. So we have replaced VPH here with this equation and F with this very equation. So by substituting, you'll get this very equation, this one, and in eta is equal to the efficiency. It is efficiency basically. So by simplifying this equation, you'll get a new value, new equation, which is given here. 1.11 into P into phi. Phi is the flux, P is the number of poles, into 3 IPH. IPH the phase current. ZPH is the phase impedance. NS is RPS, rotations per second. And this is the factor basically. Generally in transformers, we call it as window factor. So eta is efficiency, cos phi is the power factor of the motor, and it is in kilowatt, right? Now what is P phi? So here comes the role of the specific magnetic loading. What is specific magnetic loading? It is given by BAV. BAV is equal to P phi divided by pi d L. What is DL? What is D? D and L are the main dimensions of the rotating machine. What is D? D is the diameter of the rotor, right? Or stator, right? So It can be this one or it could be this one, right? And what is L? L is the length of the armature, right? So now, so here P5 has been taken equal to BAV. BAV is specific magnetic loading, right? Into pi dl, and this is kept equal to a new value Q, 3 IPH ZPH by pi d. So P into phi, in this equation P into phi has been replaced with BAV pi dl. So you have, instead of P5 you have BAV pi dl, and if you see, sorry, if you see this one, what is this? This is phase current into phase impedance by pi d. What is pi d? Pi d is the circumference basically. Okay, pi d is the circumference. So I into Z, if you remember, phase current into phase impedance divided by the circumference, it is the specific electric loading Q. It is here denoted by Q, but generally in DC machine, if you remember, we denoted it with AC. So the notation there was used is AC, but the concept is same, right? So here, when simplified, this equation means replacing I, this value by pi d is equal to Q, and P phi is equal to BAV pi dl, and 3 I P H ZPH is equal to Q into pi d. Q into pi d. So by putting it in this particular equation, you'll get a new equation which is given here. So on simplifying this also, on simplifying this equation, you'll get this pi is 2 times here, this one and this one, it is square, the specific magnetic loading BAV into Q means the specific electrical loading KW. So KW here is winding factor, sorry, not, it was not a window factor, it is winding factor. So this is efficiency, cos phi is the power factor, and D is twice here, this one and this one, so D square L. What is D square L? D square L represents the volume of the machine, and NS, so NS is the speed in RPS. Here it is given here, capital NS is in RPM, synchronous speed in RPM, right? So now from this equation, this one, this very equation, you can take all the almost constant parameter. This is 1.11, right? So it is typo here, it is 1.11, this one is 1.11. It is constant. BAV is also a constant value for a particular machine. BAV is specific magnetic loading. Then Q is specific electrical loading in this case, so it is also constant for a particular machine. KW is winding factor, which is also constant value. Efficiency for a particular efficiency machine. Okay, if you want the specific efficiency for the machine, so it would remain constant for that very machine. Cos phi is again constant, and then this is also constant. So by taking all these values here on one side, and then you have D square L into NS, which could be variables, right, into kilowatt. So this whole factor has been taken as C naught. C naught here is the output coefficient, which is equal to 1.11 into BAVQ KW winding factor efficiency into cos phi into 10 to the power minus 3. So you have the equation with you, and that equation is Q is equal to C naught D square L NS kilowatt. So that means from this equation, it is clear that the output kilowatt of an induction motor depends upon its dimensions, depends upon its volume. So even if Ns is constant, if you take Ns as a constant parameter, C naught is a constant parameter, so you can say that Q is proportional to D square L. So what does it mean? What does it mean? It means that more the volume of a machine, more is its output power. So that means if a customer says that I want, let us two machines, one is of 10 kilowatt, let us say, and second is of 20 kilowatt. So that means for the machine with 20 kilowatt, the volume is more as compared to the machine with 10 kilowatt. Okay, logically, this we understand from this particular equation, right? But again, it is in the hands of a designer how efficiently, how optimally that designer thinks of a particular design. It may be possible that you can have a high power rating machine with low volume, right? Okay, nowadays you will see that all these induction motors, specifically three-phase induction motors, they are compact, they have good power output power, they have good efficiency, so it is possible. So that all depends upon the designer. So for designer, it is a kind of problem statement, how to get an optimal design within the limited resources or within the constrained environment, right? So VPH, IPH, all these notations which are used are given here. So number of again uh, Z, sorry, my mistake. So ZPH here is the number of conductors basically. Again, I misunderstood. So ZPH here is number of conductors per phase. It is not impedance here, right? So number of turns per phase TPH, NS, and a small number of poles, specific electric loading, phi, BAVK, all are given here, right? So now the main dimension of induction motor and their separation. So meaning, because if you see in this equation, the output kVA depends upon volume. Q is proportional to D square L. So when Q is proportional to D square L, so it is a combined factor. So how can we see the output kVA with respect to the individual dimension of the motor? So the main dimension D and L are the main dimensions of the motor, wherein D is the armature diameter or the stator bore. So here in this diagram, if you can see this diagram, so in this diagram, this one, so this internal periphery, internal is the rotor and this external is the stator, right? And within this rotor and stator, this is the air gap basically. This one is the air gap between stator and rotor, right? So the diameter in this case is either the diameter of the rotor, this one, or it could be the the diameter of the stator bore, means the internal periphery, internal structure of the bore of the stator basically, right? Not the external diameter in this case, right? So L is the length of the armature or the stator core. So both are same because the length of armature and outer stator, their length is same basically, right? So these are the main dimensions, and D square L is basically the volume, which is is measured in meter cube. Now, size of the active parts of machines are given by d square L. Depends upon two factors: output coefficient d c naught and the speed ns. So, size or volume of the active parts of the machine are given by d square L. Depends upon two factors: output coefficient c naught and speed ns. For higher values of c naught, what is c naught? The output coefficient, and output coefficient depends upon these parameters: specific magnetic and electric loading, winding factor, efficiency, and power factor, right? So if we talk about these two loadings, the specific electrical and magnetic loading, we can easily understand this. So for high value of c naught and ns, means if you want high speed machines, d square L and the size of the machine will decrease. It decreases. Okay. So how from this equation you can relate d square L is equal to Q divided by C naught, this equation, this one, ns. So for the particular power, d square L means the volume of the machine is inversely proportional to C naught and ns. And volume of the machine means size of the various parts of the machine. Okay, if the size of the various parts of the machine increase, the volume will also increase, right? Thus, to obtain smallest dimensions of the machine, the output coefficient C naught must be selected as high as possible. So if you want the machine to be compact or small in size, or you want low volume of the machine, so the value of C naught means the output coefficient should be high. Okay, but it is also not that easy. Why? Because C naught depends upon BAV and Q, which are the specific magnetic and electric loadings. So if the magnetic and electric loading increase, so they have their own consequences on the performance of the machine, right? So the separation of D and L from the product D square L depends upon the ratio of L by tau, where tau is pi d by p. In induction motors, the most of the operating characteristics are decided by L by tau ratio of the motor. The ratio of core length, what is L? L is the length of the core, this one, right? And tau is basically pole pitch. Okay, so this is, we have, it is same as that of the DC machine pole pitch. So pole pitch is, it is same concept. So L by T plays a very important role in deciding the value of C naught, or you can say deciding the kind of design which we want or which we get. So here in this table, the standard values or range of L by tau is given. For example, if you want an optimized cost machine, if you want a machine with minimum cost, right? So L by tau should be equal to 1.5 to tau 2, sorry. So that means ratio of the length of the core to its pole pitch should be either 1.5 or it should be anything between 1.5 to 2. Similarly, if you want a good power factor from the machine, so the value should be between 1 to 1.25. So these all values which are indicated here have come from the research only, right? Okay, then from good efficiency, if you want good efficiency out of the machine, the value of L by tau should be 1.5. So, and if you want good overall design, so L should be equal to tau, means the length of core should be equal to its pole pitch, right? So generally L by tau lies between 0.6 to 2. It can be shown that for best power factor, the pole pitch tau is given by the equation tau is equal to under root 0.18 L. So this is the relationship between tau, the pole pitch, and the length of the core for having good power factor. Okay. The diameter of the stator bore and hence the diameter of the rotor is limited by peripheral speed. Standard constructions are employed for peripheral speed up to 60 millisecond. Now, what is peripheral speed? You all must have studied it in electrical machines. What is peripheral speed and what is rotor speed, right? For higher peripheral speed up to 75 MPS. Okay, so meter per second. Special construction method should be employed. So this is basically to have the it is related with the peripheral speed of the machine. So what should be the value of peripheral speed? Okay, fine. So what kind of design we have to select, right? So then we have specific electrical and magnetic loadings. So the definition of specific electrical and magnetic loading is same as that was in DC, which we studied in DC. So specific magnetic loading is the average flux density over the air gap of a machine. Okay, fine. The average flux, I mean distribution of flux over the periphery of the rotor within the air gap, right? Okay, and specific electric loading is the number of armature or stator, because the conductors can be placed on armature, means the rotor part, but they can be placed on the stator bore, inside the stator bore also. Okay, armature ampere conductors per meter of the armature periphery. Okay, so again it is IZ by pi d, right? And it is P5 by pi dl. Specific magnetic loading is P5 by pi dl, and specific electric loading is AI into Z by pi d, right? Then choice of specific loadings for this machine, for AC motor, the choice of specific loading means it has a very important role, because as it is said earlier also, that if you want a compact machine, the value of C node should be as high as possible, but increasing the value of C node, that means you are also increasing the value of specific loadings, right? So if you're increasing the value of specific loading, that may have its own consequences, like saturation, iron losses, or basically by increasing the specific electric loading, because the current increases, so you may have more number of heat losses, core losses, etc. Sorry, I square R winding losses basically. So now the choice of these loadings is affected by certain factors. And what are these factors? For example, the choice of specific magnetic loading depends upon the following factors. Like power factor is one, iron losses, it is same which we studied in DC machine also, and overload capacity. So the value of flux density in air gap should be small, as otherwise the machine will draw a large magnetizing current, giving a poor power factor. However, induction motors, the flux density in air gap should be such that there is no saturation in any part of the magnetic circuit. Again, the same thing, that high flux density means high risk of saturation, large losses, high losses, and large amount of magnetizing current will be drawn. So all these are the factors which affect the selection of the specific magnetic loading. Similarly, iron losses, because magnetic flux is related with iron loss on the overload capacity. So all these, for example, here for a 50 hertz machine of a normal design, the value of BAV lies between 0.3 to 0.6 Weber per meter square or Tesla. Okay, so for a machine which will be operated under 50 hertz frequency, so the value of flux density specific magnetic loading should lie between this value, right? Similarly, for specific electric loading also, right? So the factors which affect its selection are copper losses, because electric loading means current. Actually, it is current. Okay, high electric loading means high current. Okay, so high current means high copper losses. Again, voltage, small value of AC should be taken for high voltage machine. Means AC, here AC word is used for specific electric loading. So that means for high voltage machine, the value of specific electric loading should be kept minimum. Then overload capacity. So it is mentioned here that for any machine, the value should lie between 5,000 to 45,000. So this was about today's lecture, guys. If you have any queries,